So this is section 3.4 lecture for Calculus 1. And this section is more about what a derivative can tell us about a function. And this focuses on, so section 3.3 and 3.1 focused on finding the high and the low points in a function, the maxes and mins, the extrema, and also determining when a function is increasing, decreasing. Concavity deals with what we think of as the shape of a curve, the shape of the function. And derivatives can actually tell us about the shape of a graph. So that's what we'll look at today. And then also 3.4 is about what's called the second derivative test, which is just an alternative to the first derivative test, which I talk about in section 3.3. So you can actually do all of everything with the first derivative test. You don't really need the second derivative test, but a lot of people prefer it to the first derivative test because sometimes it can be less complicated to work with. The thing is that the second derivative test doesn't work all the time. And the first derivative test does work all the time. So it's kind of like a gamble to use the second derivative test, because when you use it, you don't necessarily know that it doesn't work. And if it doesn't work, you don't necessarily know that it's not going to work until it doesn't work. And then you have to go and use the first derivative test. So that's the kind of drawback of it. But it is fast. And so you do find out quickly if it doesn't work oftentimes. So, okay. So that said, here's what I mean about concavity. So like I was saying in section 3.3, we talked about when a function's increasing, when it's decreasing, and concavity, it has to do with how the function is increasing or how the function is decreasing. And here's what I mean. You can have a function that's increasing like this, or you can have a function that's increasing like this, right? Both of these functions are increasing, but one of them seems to be increasing, and its rate is increasing also, right? It starts off kind of, the function that I first drew, the one on the left, it starts off increasing at a kind of slow rate. So when you think of rate, you can think of steepness, right? Basically the steeper, the higher the steeper the curve, the higher the rate, the higher the absolute value of the rate. So notice the curve on the left, it starts off not steep at all, right? And then it gets steeper and steeper. And so this is increasing, and it's increasing. Its rate is also increasing. And when this happens, we have a curve that looks kind of like a smile, and we refer to it as being concave up. And then the curve on the right, notice the curve on the right is also increasing. But notice that with the curve on the right, even though it's also increasing, it starts off pretty steep, and then it becomes less steep. And when this happens, we have a curve that looks kind of like a frown, and we refer to this as being concave down. So again, when I think of concave up, I kind of think of a smile. And when I think of concave down, I kind of think of a frown. And here, I'm going to grab this right here. It's a candle holder. So look at the candle holder. The way I'm holding it right now is concave up. Now concave down, and there's some wax coming out, but concave up, concave down. That's concavity. So you can be increasing and concave up, you can be increasing and concave down. And then same thing with decreasing. You can be decreasing and concave up, decreasing and concave down. So you can look like this. This is decreasing. The curve is decreasing. Remember, we read these from left to right. I have to remember to clean my table because I have wax all over it now. Candle wax. So we can have decreasing and concave up. Right? We read from left to right, and we would be going downhill on this curve. And again, the concave up, that's kind of like a smile. Like if you think of the curve as a lip, as a mouth, it's a smiling mouth. Even though it's a crooked smile, it's still a smile, right? And then you can also have a curve that is decreasing and concave down, like this one right here. So by knowing when a curve is increasing, knowing when it's decreasing, knowing when it's concave up, concave down, you can pretty much sketch a curve. And this is how derivatives were used to sketch curves rather quickly. Now we sketch curves really, really quickly with a graphing calculator, but those were not so prevalent back in the day. And by back in the day, I mean like pretty recent day, like in my lifetime. So one other, so by the way, I should say, from now on, when I talk about a curve being concave up, I'm just going to use CU. And for concave down, I'll use CD to avoid writing so much. So one other vocabulary word that I want to give you is this term inflection point. This is a point where a graph changes concavity. So that means it changes from concave up to concave down, or vice versa. That's inflection point. So so you see a picture. Actually, during the early COVID days, like March 2020, April 2020, maybe it was like March 2020, I would oftentimes hear on the news, we need to reach an inflection point. We need to get to the inflection point. Because basically, this is what the COVID graph looked like the number of COVID cases. Like people became alarmed because this looked like an exponential curve. Concave up, right? The number of cases, it started off relatively low and it was growing slowly, and then all of a sudden it started growing quickly, and we end up with this curve here. And and it looks like an exponential curve, and that's alarming, right? Because exponential curves, they grow extra fast and like really quickly. And so I heard like the very beginning of this COVID situation on the news, I would hear like the scientists saying, we need to hit this inflection point. We need to hit an inflection point. And basically what they were saying is that we need for the curve to go from being concave up to concave down. So that even though the cases, yeah, there's still, the number of cases are still going to grow. We need them to stop growing so quickly. So this point right here is referred to as an inflection point. Now, it was after like the first couple of weeks, I stopped hearing the word inflection point. And I think it's because scientists knew that a lot of people don't know what inflection point is. Like a lot of people don't take calculus. And instead I started hearing, we need to flatten the curve. And that was just probably something that more people would understand. But it's saying the same thing, right? We need to hit this inflection point. Now I want you to notice this one thing. Oh, by the way, from now on, I'm just going to write IP instead of inflection point, okay? So I want you to notice this one thing. If we look at the curve, on the left side of the inflection point, our curve is concave up. And on the right side of our inflection point, our curve is concave down, right? And here's what I want you to notice. On the concave up side, notice if we look at the tangent lines, notice we start off with a tangent line that's like practically horizontal, and then it starts to get steeper. It starts to like look more like it's increasing. I think it's always increasing, but you can barely see it towards the bottom. And then, yeah, it starts to increase, and then it increases even more, right? And basically, one thing to like when in algebra, you learn the definition of a slope as rise over run. But just like intuitively, you can think of slope as representing the steepness of a line. So basically, like the steeper the line, the higher the slope. So this line, the line that I drew on the left, is less steep, right? The line in the middle is steeper than that. And the line on the right is more steep than all of them. It's the steepest. And basically, the steeper the line, the higher the absolute value of the slope. So this line has a higher slope than the line on the left. And then this line over here has the highest slope. And that's actually a rule. So like, and which you can see, like if you like imagine, it's kind of hard to see on this one that's almost horizontal, but if you imagine if you like make the run the same for all of these, I'm trying to kind of eyeball this and make the run kind of the same for all of these, although I don't know if I accomplished that for this one. Let's see if I can. So if you imagine that, like, if you like make the run for all of these the same. Run. Since slope is rise over run, excuse me. Since slope is rise over run, notice that the steeper your line, the higher your rise is gonna be. I think so like notice like the higher the rise. And so if you have like 3 fractions, I'm just gonna make up some numbers. Let's say that this is 1/3 and this is 2/3 and this is 3/3. You have like 3 fractions, right? And they all have the same denominator, but their numerators are growing. The numbers are bigger, right? 3/3, which is 1, that's bigger than 2/3, 2/3, which is bigger than 1/3. And so basically, that's a rule that the steeper the line, the higher the absolute value of the slope. So I want you to notice that the lines on the concave up part of the graph, we're going to go back to the graph. But I want you to notice that the lines on the tangent lines on the concave up part of the graph, they're getting steeper, which means they're getting bigger. And so, and basically that's gonna always be the case with concave up. If you have a graph that's concave up, that means that the slopes of the tangent lines are increasing. So on this, going back to the graph, on the left side of the graph, the left side of the inflection point, or to the left of the inflection point where the graph is concave up, the slope is the slopes of the tangent lines are increasing. Slopes of the tangent lines are increasing, which means, so go back. What is the slope of the tangent line? What is the slope of the tangent line? The slope of the tangent line is the derivative. So this means that the derivative is increasing. F prime is increasing. So this is actually all true, that whenever your graph is concave up, F prime is increasing. On the other hand, if you look at concave down, so let's look at the part of this graph that's concave down. Notice if you look at we'll look at some tangent lines. So notice we start off with a pretty steep line. And then as we go along the graph, the tangent lines become, here's me trying to draw tangent lines. Notice the tangent lines become less steep. You start off with a steep tangent line, and then it becomes less steep, and then it becomes practically horizontal. And then you might even imagine, the curve like this, right? Oops. Stop drawing what you think I'm. App, you stop drawing what you think I'm trying to draw. So if I just continue the curve like what we imagine happening, look at now my tangent lines, they start to go down, which means their slopes are negative because decreasing lines have negative slopes. So we start off at very positive and then less positive and then pretty much zero. And then if we start to go down, then we're negative. And then more negative, which means you're decreasing even more. And so just in general, whenever your curve is concave down, what that means is that the slopes of your tangent lines are decreasing. And remember, what's the slope of the tangent line? The derivative. So this means that F prime is decreasing. So we're going to put all this information together by going back to section 3.3. So in section 3.3, I made a little chart. This is what my chart looked like. It had a little column for F. It also had a column for F prime. And now for section 3.4, we're going to include a column for F double prime. And here's why. Okay, so back in section 3.3, I talked about how if F is increasing, what that means is that F prime is positive. F is to F prime as F prime is to F double prime, because F double prime is the derivative of F prime. So we can also say this: if F prime is increasing, then that means that F double prime is positive, which means, going back to what I was saying earlier, F prime is increasing. F prime is increasing when your curve is concave up. So I can say right here under my F column that F is concave. Whenever F is concave up, F double prime is positive. And then similarly, I can say, or the chart that I made in section 3.3 just said that when F is decreasing, F prime is negative. So since F prime is to F double prime as F is to F prime, when F prime is decreasing, that means F double prime is negative. And then just going back to what I was saying earlier, oh, when F prime is decreasing, my function's concave down. So this is what we have right here. And so that's basically a rule. I'm going to make a little, so in section 3.3, I had a chart for just F and F prime. I'm just going to make another chart for just F and F double prime that just has the same information. Just, I don't know if you prefer it more compact. So I'm going to write it out more compact. But basically, if your function's concave up, that means the second derivative of that function is positive. And whenever your function's concave down, that means the second derivative is negative. We're going to go and look at a homework problem that uses this information right here, this information from this chart, to determine concavity. And basically, the main thing to remember as you're working through these problems is that whenever you're talking about concavity, like concave up, concave down, and inflection points, that's basically you're doing the same thing with the second derivative that you did with the first derivative in section 3.3 when you were talking about when a function's increasing, decreasing, and finding its extrema, its maxima and minima. So it's the same processes. We're doing the same exact stuff, but we're going to be doing it with the second derivative instead of with the first derivative, as we did in section 3.3. So let's look at a homework problem. I thought number 3 was good because it's